Welcome back to the Datarekha audio guide. I'm Diya.
And I'm Arjun. Today, a trick that makes a 70 billion parameter model spit out tokens to 2-3 times faster. And the output is provably mathematically identical. No quality lost. None?
Hold on. Faster and identical. Normally, faster means you cut a corner somewhere. Where's the corner?
There isn't one. And that's the beautiful part. But let me set the stage with a real number. A team ships a 70B assistant, and in staging it's running at 1.4 seconds per token. A 200 token reply takes nearly 5 minutes. People close the tab before the first sentence lands.
So why is one token so slow? It's just predicting the next word.
Because to predict that one word, the model has to read every single weight it has out of GPU memory. For a 70B model, that's 140 gigabytes of data moved per token, and it's strictly sequential. Token 5 can't start until token 4 exists. The chip spends most of its time just waiting on memory, barely doing any actual math.
Okay, so generating is expensive. What's the way out?
One insight that flips everything. Checking a token is far cheaper than choosing one from scratch. The big model can take a whole batch of already written tokens and, in a single forward pass, score what it would have said at every position, all at once, in parallel. Same memory read, but now you're verifying 4 guesses instead of producing one.
So I need someone to write the guesses cheaply. That's the second model.
Exactly. You pair the big target model with a tiny draft model, say a 1B alongside the 70B. The little one sprints ahead and proposes 4 tokens, fast, maybe 50 milliseconds. Given the cat, it guesses sat, on, the, mat. Then the big model checks all 4 in one shot.
Give me the picture. What actually happens when the big model disagrees with one of those guesses?
Think of an editor with a fast junior writer. The junior drafts a whole sentence. The editor reads it in one pass and runs a red pen down it. The cat sat. Fine. Then, on. No, I'd have written something else. The moment the editor rejects a word, everything after it gets thrown away. The editor writes that one word himself, and the junior starts the next sentence from there.
So the worst case is the junior is wrong on word 1, and then you've basically just done a normal step.
Right? You still got one real token, same as baseline. But when the draft is good, you bag 3 or 4 tokens for the price of a single big model pass. In practice, a well-matched draft gets 3 or 4 out of every 4 accepted. And that's your 2-3x speed up.
Now back to my corner. If the small model is sometimes wrong, how is the final text identical to running the big one alone? Surely the cheap model's bad taste leaks in.
It cannot. And this is the part most explanations skip. The accept to reject step isn't a vibe check. It's rejection sampling. You accept a guess token with a precise probability. The target's probability divided by the drafts. And when you reject, you don't just drop it. You resample the replacement from a corrected distribution. The targets minus the drafts. The math guarantees the tokens you keep are drawn from exactly the target's distribution.
Oh, so the draft model only ever touches the speed dial, never the answer. A genuinely terrible draft just gives you a 1x speed up. It can't make the model say something wrong.
You just stated the whole theorem. Draft quality controls the acceptance rate and nothing else. There's even a clean formula. Tokens per big model pass is roughly k times alpha plus 1. K guesses, alpha the acceptance rate. And the plus 1, because you always get at least one token. 4 guesses at 80% acceptance is 4.2 tokens a pass instead of 1.
And what makes that acceptance rate high or low?
How well the draft thinks. Like the target. Same training flavor, ideally a distilled smaller cousin. And the text itself, predictable stuff like code or legal boilerplate, gets accepted almost every time, so it flies. Wild, open-ended creative writing is harder to guess. So the rate drops.
Is there a way the whole thing quietly corrupts the output instead of just being slow?
one real trap. The two models must share the exact same tokenizer. If the draft chops text into different pieces than the target expects, the positions don't line up. Verification compares the wrong things, and you get garbage. So you can't just bolt any small model onto any big one. And if a deployed chatbot's wording suddenly drifts after enabling this, mismatched tokenizers is the first suspect.
And there are newer versions that skip the separate draft model entirely, right?
There are Medusa bolts extra little prediction heads onto the big model so it drafts for itself. Eagle, the strongest. Now the default in a lot of serving stacks, does something cleverer. Instead of guessing the next token, it guesses the model's next internal hidden state, which turns out to be an easier, smoother thing to predict. So acceptance climbs. And Ingram drafting needs zero training. It just notices a phrase repeated earlier in the context and replays what followed. All of them keep that same exact output guarantee.
So the one line to walk away with.
Let a cheap model guess and an expensive model grade, and prove the grading is exact. You buy speed with the draft's accuracy, never with the answers. That's the Datarekha audio guide. See you in the next one.